Topic video 4, Introduction to Input and Output, and an in-depth look into general purpose input-output subsystems. So, what is input and output? Input refers effectively to any information provided to the microprocessor from the outside world. So, any sort of stimulus from the outside world that we're using inside our processor is considered to be input. Output, of course, is any information that we pass from the microprocessor back to that outside world. So if your processor has no form of input or output, then effectively the processor is blind, deaf, mute, and paralyzed. It's effectively useless if you don't have some sort of input or output. So generally in every microprocessor application, there will be some sort of input or output. What sort of form that input or output is depends on the application, but there will always be some form of input and output. Okay, so the microprocessor must be able to receive information from the outside world, so it must be able to have some sort of input, and of course the microprocessor must be able to return those results or of any calculations back to the outside world. So effectively a microprocessor is nothing more than a transformer of input from one form to some sort of output. So the processor just transforms the input from one sort of form to another form, and that becomes the output. So a microprocessor generally will have one input and one output, whether that output is simply storing it back into memory, as if it's like a data logging mechanism, but still it has some sort of transformation of that input and then some sort of output, whether it's back out via a device, output device, or whether it's into memory, but it has some output of some kind. So when it comes to input-output devices, we can have many different I/O subsystems built inside a microprocessor. There's two possible ways of accessing those subsystems. One, it can be a ported I/O, which means we have access to the device through a small port or memory. Okay, so it's generally through a general purpose I/O port. So effectively in ported I/O, we're effectively dealing with an input-output device through a very small window, so it's generally like a general purpose I/O device. So we might be going through this very small window of registers to simply then see a larger set of registers. So I guess some examples of ported I/O may in fact be when we talk to the LCD device in experiment 2. The LCD device has its own local memory, has its own local instructions, and we simply control that device through that very small window, which is those two general purpose I/O ports. Of course, there's also other devices. When you deal with SPI devices, there's digital to analog converters, which have their own instructions, they have their own memory, and effectively using through that small port, which is the SPI device, you're simply dealing with that external device. So we can have ported I/O. Ported I/O has small finite I/O space, has separate memory space, has separate instructions for the I/O, so you're actually going to deal with it using different instructions. The other alternative, which is a better alternative, is memory mapped I/O. So therefore the entire device, including all its internal registers, are mapped into consecutive memory locations in the memory map. So an example of memory mapped I/O is of course all the internal subsystems inside our processor. So all our SPI, our serial, our analog digital converters, they all have their entire register set mapped into our memory space in the lower 2K of our memory. So the beauty of that is that we have no separate I/O space. We can make use of our entire global memory to cache values for that particular I/O subsystem. We also have a lot more space, as I said. We can make use of our own space. We have the same instructions for the input-output, so therefore we can simply use our normal mnemonics to simply get that I/O subsystem to do what we want it to do. So we can move data around from memory to that I/O subsystem just simply by using our standard move, load and store commands that we have at our disposal, whereas when you're dealing with ported I/O, you may actually have to move data around by using a specific bit sequence that you've got to pump to the device. So memory mapped I/O is of course a lot easier to use than ported I/O. But you have those two different forms, and you've got to be very careful when using them that there are these limitations that are sort of implied. So as I said before, Our internal subsystems are all memory mapped I/O. They're all mapped to the lower 2K of our memory. So in the lower 2K of memory, we have our entire register set. So we have port A, port B, directional data register for port A and port B, all in the lower 4 bytes of our memory map. So therefore, we can access these general purpose I/O components simply by jumping to those memory locations, or simply storing values in those memory locations in our memory map. We can configure those two devices. So effectively, all our internal subsystems are all mapped to that lower part of that memory map. So when it comes to input-output subsystems, there are generally two basic types of I/O. There are, of course, serial and parallel subsystems. So when it comes to serial devices, these generally use only one data pin on our microcontroller. Okay, the data is transmitted via a shift register out this pin, 1 bit at a time. So generally when dealing with these subsystems, we load the data in a parallel form. The subsystem then rips that parallel form down into a serial fashion simply by pumping that data out of a shift register 1 bit at a time. And because we're shifting them out 1 bit at a time, we can in fact configure the serial subsystem to either shift it the most significant bit first or the least significant bit first. It doesn't matter which way you shift it, as long as the mechanism at the other end is reconstructing it in exactly the same way. So if you, serially talking to a particular chip, say an SPI chip, and then SPI chip says it needs it in a particular fashion, then you've really got no choice but to shift it out in a similar fashion out of your serial component on your processor. So the rate at which the data is transmitted and received depends on some prearranged clock frequency. So we can actually shift the data in and out of that shift register at a prearranged frequency. So the serial interface can either embed its clocking information into the data it's transmitting, or it can use a separate pin to pass that clocking signal. So depending on whether you're using a asynchronous serial communication, then in fact the clocking information is prearranged at both ends, and we're simply just phase aligning that signal each time we send some data across. Or in fact you can simply have have the master generate the clock signal and then simply pump the clock signal to all the other devices, so therefore they don't have to locally generate their own clocks. So it depends on whether it's asynchronous or synchronous, and we'll talk about that a bit later on when we talk about serial subsystems. So some of the most commonly used serial mechanisms are RS-232, and this is commonly referred to as asynchronous serial. This is the most common serial interface that is provided on many microprocessors and computers. Provides bit rates up to 115 kilobits per second, and the clocking information is embedded into the data. Generally has a 3-pin interface, RX, TX, and ground. So we're going to ensure that we have a common ground, so therefore our digital signals are all interpreted in the same fashion. Another commonly used serial subsystem is SPI. It is a serial subsystem interface commonly found on microprocessors and microcontrollers. Provide bit rates up to 4 megabits per second. Has a separate clock line, so it's generally a 4-pin interface. Has an output pin, an input pin, master in, slave out, an output pin, master out, slave in, clock line, S clock line, and ground. So have a 4-pin interface. Then we simply, using that 4-pin interface, we can hook that up to any sort of SPI-enabled component. I2C is also another commonly used interface on microprocessors. It's called the Inter-Integrated Circuit Communication. It's an interface, as I said, found on some microprocessors. Provides speeds up to 100 kilobits per second and has a separate clock line. So it's a 3-pin interface, has an SDA, SCL, and ground. Okay. We also have a CAN bus, which is a serial bus that's used effectively, it's controller area network. It's primarily used in control applications, so in a lot of, plant situations where a lot of the plant mechanisms might be automated, they'll be controlled by a CAN bus. So it's a differential serial system used in control applications, as I said. It can operate up to 1 megabits per second. It's robust against noise and basically has a 5-pin interface. The reason it's robust against noise is because it uses differential signaling. So we have 5 pins. These pins are RX-CAN plus, RX-CAN minus, so there's the differential. So we have positive version of the signal, we have a negative version of that signal being transmitted at the same time. We then have TX-CAN plus and minus as well, and we have a ground, so that is our 5-pin interface for our CAN serial mechanism. And of course the other types that we have, of course, parallel. And when it comes to a parallel interface, generally we're trying to write whole bytes or words to the outside world at a time. Okay, so we're simply pumping out an 8-bit data out of an 8-bit general purpose I/O port. So we can simply pump the data out in a parallel fashion. Of course, we can pump it out quicker. Okay, but of course there's disadvantages to that. So general purpose I/O doesn't really require any complex hardware to transmit or receive the information. They do not require a clocking signal to reconstruct the information at the other end. It's simply parallel, simplest form of I/O that you can actually get. So these interfaces are simple and very quick to transmit information. However, these parallel interfaces come at a large cost. They consume pins on the processor very quickly. So if you've got, say 10 8-bit GPIO subsystems and you want to use them all, then effectively you've chewed up 80 pins. Okay, so you've used your pins up very quickly, whereas if you've got a serial subsystem, it's only got 3, 4 pins tops. So therefore you can have double the amount of. So if you've got an SPI interface, you can effectively have 2 SPI interfaces shipping out information at 4 megabits per second instead of having one 8-bit GPIO line. So effectively, serial reduces the pin count, parallel simply chews up our pin count very quickly. And if you've only got an 8-pin processor like one of those U-boot 8-pin PICs, then of course you don't even have that number of GPIO lines anyway. You've only got top of 6 general purpose I/O lines, and if you use all 6 of them, then of course you've used up all your input-output components of your processor. So parallel GPIO is very costly as far as pin counts are concerned. Okay, and of course general purpose I/O is of course an example of parallel interfaces. These are primarily our means of getting data in and out of our processor in a parallel fashion. So we call it general purpose input-output. Okay, so when we communicating with I device can be achieved using 3 different methods. One is we can do programmed I/O, which means we can simply, the transfers take place under software control, so the processor accepts and delivers data when the software dictates. So we can do programmed I/O, so simply the program dictates when data is moved around. Okay. Interrupt-driven I/O. This is effectively when external events take place. When data is read or written from the I/O device, the program flow is halted to deal with that particular event. So we have some external event saying that simply we have, I guess, a subsystem that's received some data and said, hey, I've got some data. Hey, processor, stop doing what you're doing and deal with this. Do something with this data for me. So we actually have external events that then dictate when data is actually being processed. So therefore the processor is forced to stop whatever it's doing and deal with that data that's now been made available. Okay, so the I/O devices effectively contain a control line which is called an interrupt line, so therefore a device is actually able to trigger an interrupt via this IRQ or int line that they have. So a particular subsystem may receive some data, say, hey, I've got some data. It informs the processor that it's got data by simply firing a signal down this interrupt line. Okay, and then of course so therefore when that device has an interrupt, basically has a bit of data that the processor needs to deal with, it drags its interrupt line low, causes the processor to stop what it's doing, and simply makes the processor service that sort of request. So therefore now we're not dictating when data is moving around by simply the code telling it when it moves. We're now moving data around when external devices tell us it needs to move. So therefore some data has been received by the processor. The processor says, hey, I've got some data, deal with it for me. So now the process is being dictated to by an I/O subsystem. So to give you an example of that, we have an RS-232 serial subsystem that reads in serial information. Okay, it reconstructs the byte, makes it available in a data receive register. So simply we have data being pumped down to our processor in a serial fashion. The shift register is reconstructing it at the right rate. So after 8 serial shifts, we've simply got an 8-bit value that's simply pumped out to a data receive register. Okay, and because our serial data is constantly piped down that line, so it's constantly being reconstructed. So if we don't deal with that data within the next 8 shifts of that shift register, it's effectively going to be overwritten. So we need to sit there waiting for a bit of data to become available and then simply grab it when it's available. Okay, or we can simply do whatever we want to do, and then when there is data ready to be read, I guess, we can have the serial subsystem say, hey, I've just got an 8-bit chunk of data, I need you to do something with it quickly, you've got 8 clock cycles before I override it. So therefore you can actually have, therefore that serial subsystem will then trigger an interrupt, say, hey processor, stop what you're doing, I've got 8 bits of data, do something with it quickly. So therefore the processor can stop what it's doing, grab that 8 bits of data out of that register, probably store it in some other memory location, and then go back to doing what it's doing. And then when it gets a chance, can then go back and process that 8-bit character or whatever it was it got off the serial port. So it needs to be able to deal with that data being made available before the next bit of data overwrites it. So it's effectively interrupt driven. So it's a serial subsystem that's then dictating to the processor when it needs to move that data out of the register, the receive register, and basically telling it needs to do it now or it's going to lose it. So the RS-232 subsystem can be set up so that it triggers an interrupt when there is new data to be read. So you can actually configure that serial subsystem so when new data is available, it triggers an interrupt which causes the processor to actually deal with that data. And therefore the processor is forced to deal with that data before it's overwritten. So if the if the processor wasn't equipped with interrupts, the data would simply arrive. If it didn't read it within those 8 clock cycles, it'd be overwritten, so we'd end up losing data. So if the processor was trying to dictate when data moved around, it effectively would end up losing data because it would be unaware that the new data arrived in the serial port, wouldn't grab it in time, and we'd end up losing data. So therefore, in this case, the serial subsystem actually dictates to the processor, hey, there's new data, deal with it, and then grab it now, do something with it before the next byte arrives and overwrites it. So if it's interrupt driven, then we can ensure that data isn't actually overwritten. We can also do DMA transfers. So this is where we start transferring data without putting any sort of heavy overhead on top of the CPU. So we can simply say, got a lot of data I need to move around, and therefore it can happen without the CPU even being involved. So DMA consists of multiple channels. Each DMA channel has associated with it a 16-bit address register and a 16-bit count register. So to initiate a data transfer, the device driver effectively sets up the DMA channel's address and a count register together with the direction of the data transfer, whether it's read or write, and simply then instructs the DMA hardware to begin that transfer. So the CPU sets up the transfer, but then the transfer takes place without the CPU being involved. So DMA transfer is a good way of like moving big chunks of data around without the CPU actually having to go load, store. You can simply set up the DMA to move it around in big chunks. So a lot of microprocessors actually have DMA or eDMA subsystems that you can utilize to move big chunks of data around. Our processor, of course, doesn't have a DMA channel, but it is available on a lot of DSP processors. So when it comes to I/O and our processor in particular, our processor is capable of various modes of operations. The most common mode of operation is, of course, single chip mode. And when you put it in single chip mode, and it's the mode that it's in by default, and unless you rip the processor out of its box and start playing around with the jumpers, you can't actually change it out of normal chip mode. So normal chip mode is the mode it's currently in, and it's the mode it's happily going to stay in. But when it is in single chip mode, effectively that's defining that you only need the single chip to be able to do everything you need. So when it's in single chip mode, you're basically saying, I have everything I need on this single chip. So I have all my memory that I require for my particular application. I have all the subsystems that I require for my particular application, all contained inside this nice little quad flat pack. Okay, so therefore single chip mode defines that you don't need any external buses. Okay, if you turn it to the other modes, which are extended modes or expanded modes, you can actually then make the address and data lines available outside of the chip. So if you want to be able to have access to the address and data lines outside of the chip, which means you might want to actually memory map in some additional components, then you can effectively put it into expanded mode. But by default, it's actually in normal chip mode, which means you've got everything you need inside that single chip. Okay, so programmer's I/O model. And when I talk about all these various subsystems, I will talk about their programming I/O model, because the programmer's I/O model is effectively your interaction as a programmer effectively with that particular subsystem. So our interaction with these subsystems is all via a series of registers, memory mapped registers for a particular subsystem. So we contain, basically inside our processor, we have numerous I/O possibilities, including parallel, serial, and analog interfaces. Okay, and all of these internal I/O subsystems are mapped to the lowest 2 kilobytes of the memory from 0 to 7FF. So as I said before, when I showed you that memory map, all our I/O registers are actually mapped to the lower 2K of our memory. Our processor, our MC9S12XDP12, contains 12 8-bit general purpose I/O ports, and the pins of each of these general purpose I/O ports are shared with other I/O subsystems. So if you're using a particular I/O subsystem, like say a serial subsystem, then you've got to be aware that you can't use the associated general purpose I/O port. So if you use the primary or auxiliary serial RS-232 serial ports, then effectively you can't use the port S general purpose I/O port. So a lot of these general purpose I/O ports actually have shared purposes with various subsystems. So you've got to be careful that if you're using that subsystem, you can't use its associated general purpose I/O port. Okay, so basically on power up, all the general purpose I/O ports are enabled by default. All of the other I/O subsystems are disabled. So if you need to use a serial subsystem or you need to use an analog subsystem, then of course you've got to enable it, because by default they're off. So I've shown here a table of all the various ports that we have at our disposal. So these are all the general purpose I/O ports we can use, and I've also shown their actual physical pins that they actually live on the headers. So we have, you know, port A, port B, port J, and their various pins that we can use. Okay, so the other thing that you're going to be aware of is that some of these ports, we don't actually have access to all their pins. So you'll notice, like when it comes to port M, we only have access to 4 of the pins of port M. So not all of the pins are actually wired up to the headers. So you're going to be aware of that as well. So the GPIO subsystem is responsible for maintaining the general purpose I/O ports. Okay, and basically that general purpose I/O subsystem is called our port integration module. So if you're looking in the data sheet for the section that refers to general purpose I/O ports, well, effectively it's called the port integration module. And basically the port integration module, as I said, is responsible for all the GPIO ports that are in our processor. Okay, so it's responsible for ensuring that the GPIO and the particular subsystem that also uses those pins, they don't conflict. So it sort of makes sure that if you turned on the IOs, the particular subsystem that shares those pins, then of course the port integration module is no longer available for that particular port. And then of course if you turn on the general purpose I/O port, then of course the port integration module ensures that the I/O subsystem that shares that port is also turned off. So sort of make sure that you can have one or the other, but not both. Okay, so general purpose input-output allows 8-bit data to be driven onto the physical pins of the microprocessor and read from the pins via a data register. So we can actually have values being driven onto the external pins and have those, I guess, logical equivalents or whatever voltage value driven on those pins appear in a data register. So if the GPIO port is set up purely as output, then any value that you write to the general purpose I/O port's data register will appear on the 8 pins associated with that port. So in the top orange example I've got here, it's set up as output, which means we can simply put logical values in that data register, and then the appropriate voltage values will appear on those actual pins. So in the example I've written 111000101 into that data register. Therefore on the pins associated with that data register I get 5 volts, 5 volts, 5 volts, 0 volts, 0 volts, 5 volts, 0 volts, 5 volts, which are the equivalent of the TTL logic levels. Okay, so if the general purpose I/O is purely set up as input, as in the yellow example on the bottom, then any value that we drive on those physical pins, and in both examples those grey boxes are the physical pins, any value we drive on those physical pins will in fact appear in the data register. So therefore, if I drive voltage values of 0, 5 volts, 0, 0, 0, 5 volts, 5 volts, 5 volts onto the actual physical pins, then in the data register associated with that port, I will get 0, 1, 0, 0, 0, 1, 1, 1. So I'll get the equivalent logical values that represent the TTL, voltages that are pumped into those pins. Okay, so therefore the data registers will effectively mimic whatever is being put on those pins. And the thing you've got to keep aware of here is that the bit location is specific for a particular pin. So the most significant bit in this particular port, let's say that in the orange up the top there, the orange example, let's say this is port A's data register. So therefore the first bit there, which is the most significant bit, would be PA7. Therefore that value of 1 would actually then drive 5 volts to the pin called PA7. The least significant bit of the orange example, that would be PA0. Therefore that 1 there would actually drive a value out to the actual physical pin called PA0. Okay, so you get 5 volts on PA0. So the actual bit locations are directly mapped to the physical pins of that particular port. So when it comes to using the general purpose input-output, it is general purpose input-output. So it means we can actually get data in or out. So therefore there needs to be some sort of mechanism of controlling whether it's in or whether it's out. So using general purpose I/O ports, we can effectively set them up to be 8-bit input, 8-bit output, or any combination in between. So we can set top 4 to be input, bottom 4 to be output. We can set every odd bit to be input, every even bit to be output. We can configure it however we want to. Okay, so we can do bitwise configuration of whether each pin is either input or output. Of course, the direction of each of these pins in the general purpose I/O port can be defined to be either input or output, and we can define whether they're input or output by using the data direction register. So every port has a data directional register, and with using the data directional register we can define the direction of that particular pin. Okay, so therefore each general purpose I/O port has 2 registers so far associated with it: a data register, which we can use to write data out or read data in from, and a data directional register, which we can use to define the direction of each of those pins. So I've shown in the figure on the right how the data and the data directional registers actually relate with one another. So you can see that the data directional registers are connected to 2 buffers, and depending on the value in the data directional register will define the direction of that particular pin. So you can see that if we put a 1 in the data directional register, then effectively the pin at that bit location in the data directional register will effectively become an output. If you put a 0, then that particular pin will become an input. So therefore, not only do we have the bit locations in our data register define the particular physical pins on our processor, we also have the bit locations in our data directional register then defining the direction of each one of those physical pins on our processor. So to show that a bit more clearly, in the blue we have our pin, which we call PTX7. So we don't actually have a port X, but this is X as in replace it with any particular port that you want to talk about. So we simply have our data directional register for pin 7 is set to be 1, which means we actually have turned on the output buffer. So therefore any value we write in the data register in that bit location of 7 will simply be echoed out of that particular pin. Same thing when on the green example, when we put a 0 in there, then effectively we make it an input pin. So therefore whatever we echo on the particular physical pin will in fact be reflected inside the data directional register as a logical value. Okay, so when it comes to our general purpose IOs. All of our registers for our general purpose IO are actually mapped into our memory locations. Okay, so we have the data registers, and the data direction registers can be set in the same way as writing any particular value to a memory location. So as long as you write that value, so a particular value to the right memory location, effectively will configure the general purpose IO to function however you want it to. Okay, so you can either access these registers via their actual memory location, as I've shown here, or by their name, and I'll put their name in brackets. It's usually easy to do it by their name because, as I've said before, if you start using names, then it makes your code a hell of a lot more readable. Instead of using magic numbers, try and use as many names as possible. It also makes your code portable as well. So if you use the names and you move your code from one processor to another, the IO registers might be in different locations, but if you're using the same software but on a different platform, then it's a good chance that they'll be using the same names, but then they'll map those names to different locations for you. So it's always better to use their names. So some examples of using general purpose IO. So in these two examples here, I've used port H. So I've loaded my accumulator A with FF. So effectively, I'm going to want to store that into the data directional register of port H, and by putting FF into DDRH, I've effectively made port H an 8-bit output port. So if I write AB to the pins of port H, so therefore I store it into PTH, therefore the actual value AB, so the bit representation of AB, will actually appear on the 8 pins of port H. Okay, so I'll end up with 10101011 on port H. Of course, I can also set up port K as a total input port, so I can do a clear DDRK, and therefore by doing a clear DDRK, it's simply zeroed the data directional register for port K, which means they're all now inputs, and therefore I can simply read a value from port K simply by loading accumulator A with the data register, which is port K, and therefore I'll have whatever is sitting on those pins of port K now reflected in its logical representation in accumulator A. So another example, what I can do is I can actually set up port H. So I can set the top 4 nibble up as output and the lower 4 nibble up as input. And therefore I can then store that value onto the data directional register, and therefore set up that actual port H as top 4 output, bottom 4 as input. So therefore I can then write AB to the pins of port H. So if I do move AB to port H, the one thing you've got to be aware of is when I do a store onto a port where only part of that port is input and part of that port is output, effectively only the only the output bit of that port is actually modified. So by writing AB to that register, it's only the top 4 nibble that actually changes. Okay, the bottom 4 nibble is only read-only because it's input. So therefore if I write to the bottom 4, it's just going to ignore it, because the bottom 4 will always reflect whatever is on those physical pins. So therefore whatever's on pin PH0 to PH3 is always going to be reflected in the lower 4 nibble. And therefore if I read back from port H, then I'll basically read in the entire 8 bits of port H, which means I'll read in the top 4 that I've just stored there. So the top 4 bytes will be the A that I've just stored there, and the bottom 4 bytes, so the bottom 4 bits will effectively be whatever is currently being pumped onto those 4 pins. Okay, so that's something you've got to keep in mind, is that if you set a port up to be both input and output and you write something to it, it is only the output pins of that port that actually change. The input pins will always reflect whatever is currently being driven onto those pins by the outside world. Okay, so when it comes to general purpose input-output, we have a series of input and output pin electronics associated with them. So because it is an electrical device, you've got to keep that in mind when connecting it to other devices. Generally, it's always a good idea to set any unused input pins to be either ground 0 volts, or to VCC, which is 5 volts. So you either put them high or put them low. So if you set a put up as an input, you're not using it, then tie them high or low. And this will cause the pins from causing unpredictable errors, so it will stop pins from jumping around from random states. It's also important to ensure that basically any unused output pins, so if you're not using any, so if you set up a port to be output and you're not using them all, any of those unused pins, leave them floating. It's very important. Don't ground them or don't VCC them, because you can get some really disastrous things happening. If you've got an unused output pin and you connect it to ground, or you connect it to VCC, and then you put the opposite logic value on that pin. So if say you ground a pin, and then you put the logical value of 1 on that particular pin, which is going to translate to 5 volts, then effectively you've got a short circuit. You've got 5 volts going to ground, and because you don't have a resistor there, you're effectively going to cause it to chew up a lot of current. So what's going to happen is the maximum amount of current that pin can provide will be reached, and as a result of that, the processor will get hot, which in turn will cause it to then generate more current, which in turn will cause it to get hotter again. So therefore, the temperature of the processor will actually exponentially run away to the point that it reaches the maximum temperature the processor can handle, and of course then it starts to burn, and you'll end up frying the chip. So it's always a good idea to leave any output pins unconnected. Okay, if you're really paranoid, make any unused output pins inputs, and then if you do connect them, it's not really going to be a major problem. So we want to ensure that we don't have the phenomenon known as latch up occurring, which causes the processor to draw the current and simply burn out. Effectively, to ensure that latch up doesn't occur, we have associated with our general purpose I/O, we have a series of pull-up resistors associated with it. So if you have an output pin that's not connected, it will generally pull up. Okay, and therefore if you accidentally, connect an output pin to ground and you simply pump the other voltage, the opposite logic value through it, it's not going to drain a whole heap of current, because you've got that pull-up resistor there limiting the current flow, and therefore latch-up will not occur. Okay, so we've got these pull-up resistors to enable that extra level of protection to ensure you don't blow the processor apart. So the pull-up resistors ensures the safety of the processor. However, the pull-up resistors slows down the responsiveness of the general purpose I/O pins, and also increases the power consumption of the processor. Okay, therefore it's possible to turn off or turn on each of these pull-up resistors. By default they're on, but it's possible to turn them off if you want to increase the responsiveness of that pin, or you want to reduce the power consumption. But of course, if you turn them off, you've got to be extremely careful, because you can cause serious damage to the processor if you turn them off and you do something wrong. So please do not touch the pull-up resistors settings. Okay, so leave them well alone, don't touch them, because you turn them off, you can start blowing things up. The other thing with the general purpose I/O port is, normally we want to, when we're doing output on the general purpose I/O, we need to connect this up to some sort of electronics on this other side. So general purpose I/O is effectively going to drive some sort of device. So some devices require lots of current, okay, and some devices require very little. Okay, providing lots of current to a device ensures that we have fast switch times. Okay, however, we consume a hell of a lot of power. Okay, by default the GPIO pins are set for high drive current operation. Okay, but if a device doesn't need lots of current, or it doesn't need fast switching, then reducing the drive would also reduce the amount of power that you consume. So if the processor, we were using this processor in a mobile application, then each bit of power is extremely important. So you might want to turn on reduced drive for that particular port. Okay, so it's possible to turn off the high drive of a general purpose I/O port simply by putting that pin into a reduced drive mode. Okay, so there's actually each general purpose I/O port has a reduced drive control register associated with it. So you actually turn each one of the pins to be reduced drive if in fact that pin doesn't require it. So therefore you can make better use of your power. So basically, each one of the general purpose I/O ports on our processor has associated with it a data register called port X or PTX. So some of the registers are actually called port and then the letter. Some of them are called PT and the letter. But look at the table to see how they differ. The data directional registers are always called DDR and then the letter of the port. And then we have reduced drive control registers. Some general purpose I/O ports have their reduced drive registers associated with another control register because effectively they turn all, either you have the port totally in reduced drive mode or you don't. So some ports actually don't give you pin-wise configurability, but it depends on which port you're using. Okay, when it comes to writing input-output software, generally our input-output software consists of three major components. Okay, we have our initialization, we have our data input or output, so we initialize the port, we simply input or we output some data to some particular device, and then we have some sort of software synchronization mechanism. So we need to ensure that if we're going to use a general purpose I/O to bit bash out to a device, we don't just continually hammer that device. We need to enforce some sort of delaying or synchronization mechanism to ensure that we talk to that device at the rate that it actually wants us to talk to it. So of course the software must be synchronized with the reading and writing timing requirements of that particular connected device. Generally microprocessors are a lot faster than attached input-output devices, so the processor must be synchronized via software and hardware techniques. And possible techniques include real-time synchronization, polled I/O, and hardware handshaking I/O. And I'm going to go through a few of these examples. But before I do that, I might just reiterate something that you should be familiar with, okay, which is timing diagrams. So timing diagrams are very, very useful for understanding how you need to communicate with devices. So if you're going to do some sort of synchronization in software to talk to a particular device, you've really got to understand its timing diagram. Okay, so the timing diagram illustrates visually the relationship between the I/O signals of an I/O device, and the various signals of the I/O device are represented by square waves in a timing diagram of varying periods, and it's basically the relationship between corresponding signals that is the most important thing that you've got to keep in mind. And of course this relationship can be easily seen inside a timing diagram. So we have here a very simple example of a timing diagram. So this is just simply for a logic gate. You can just simply see A, B, and what happens to F as a result of A and B. So you can just simply see the relationship of the input, the output with respect to the inputs. However, we have a more complicated timing diagram here, which is in fact the timing diagram for the LCD that you use in experiment 2. And what we can see out of this timing diagram is we can see the relationship between the various control signals. You can see that you need to set the RS line and the RW line. And then once you've set those lines, then you need to strobe the enable line high. Once that's high, then you can set the data lines, and then you can bring the enable line low. But one of the most important things to see about this timing diagram is the time that must be waited between each of these events taking place. So you'll see that there's timings that show how long the enable line has to be high, how long you have to wait before you can trigger that enable line high. So after you set RS and RW, how long do you have to wait before the enable line goes high? So there's all these little specific values that are told to you from this timing diagram. So you've got to keep these in mind. If you want to successfully communicate to that LCD device, then you've got to be able to decode this timing diagram. So therefore you can get your software to mimic this timing diagram. Okay, so when it comes to real-time synchronization, and this is the first way that we can do software synchronization, real-time synchronization uses software delays to match the timing requirements of the software and hardware. So we try to match our software to the particular hardware device that we're trying to talk to, and we do this using delays of some kind. Using real-time synchronization has its problems, of course. No idea is without its flaws. The delays are generally generated by instructions and therefore cannot be exact due to errors caused by instruction execution overheads. So we don't have exact delays that we can generate, but we're dealing with approximate delays. The other thing is, because we're using instructions to generate these delays, therefore the sort of delays we can generate are multiples of our instruction cycle. Okay, therefore if we want delays smaller than an instruction cycle, we just can't do it. Okay, so some common delay structures that I'm going to talk about. If you're doing very, very, very small delays, and I mean by very small delays, I mean something of only a few instruction cycles, then we can use our NOP instructions, a sequential series of NOP instructions to enforce that delay. So if it's only a small number of delays that we need, the small number of instruction cycles we need to delay by, then simply just use a series of NOPs. Okay, so if we've got slightly larger delays, so we need delays of less than 1021 instruction cycles, okay, then we can start using slightly bigger sort of structures. So now we can start using a for loop, so to speak, to do a delay for us. So I've given you here a chunk of code that does a for loop. So simply we load accumulator X with a value, and then we simply dec A and we branch if not equal back to loop. So one thing to keep in mind here is I've actually noted down here how long each one of those instructions takes in instruction cycles. So one thing to keep note of here is that in order to load accumulator A with the value of X is going to take one instruction cycle. To decrement accumulator A is going to take one instruction cycle. To branch back to the loop label is going to take 3 instruction cycles. If we don't have to branch, then that's going to take 1 instruction cycle. So therefore, running this chunk of code, the total delay that we're going to achieve by running this chunk of code is effectively going to be 4 times whatever the value is that we make X, okay, minus 1. So I've given an equation there that we can calculate the total delay of that code by simply adding up the total number of instructions. So the total delay of running that code depends on the value of X. If we got slightly bigger delays, less than 262,000-ish instruction cycles, then we can simply do the same structure we did before, but now we'll just use a slightly bigger register. So instead of using an 8-bit register, we'll simply use a 16-bit register. So therefore that means we can now have a larger value for that X parameter. One thing you've got to take into account here is that when you load accumulator X, it takes 2 instruction cycles to do that. And then when you decrement, it takes 1. When you branch, it takes 1 if it's false, it takes 3 if it's true. So therefore, most of the time it's going to be true. It's only the last time that it's actually going to be false. So therefore, the total delay is the same as the previous one. It's simply 4 times X, but there's no minus 1 because it's taken an extra instruction cycle to actually load the index register. So it's simply 4 times X to generate the total delay that we will have by running this chunk of code. So therefore, we can actually use this to perform a certain delay because we'll know what the total delay is. And therefore, we can take the total delay, we can divide it by 4, and we can simply find out what the value we need to load into X is. However, if we actually need bigger delays even more, so delays greater than 262,000 odd cycles, then we can just simply do a nested for loop. So we can simply use 2 index registers, Y and X, and we can simply loop inside the inner loop until our X value drops down to 0, and then when X value drops down to 0, simply go back up, and we simply do the outside loop once, which means it resets our X value back to its original value. So we simply end up doing, that X loop Y number of times. Okay, so therefore we've got the instruction cycle count for each one of them. So I've simply gone and calculated the total delay, which is going to be 4 times Y plus Y times 4 times X. Okay, so that's the total number of instruction cycles that it's going to take for us to run that chunk of code. So to give you an example of some real-time synchronization, let's say we want to drive port PH7 in this particular fashion. So we need it to be low for 750 nanoseconds, high for 2.5 microseconds, and low for 120 milliseconds. Okay, so that's going to cause us to use all the different various mechanisms we've talked about. So first one, we've got 750 nanoseconds. We divide that through by our instruction cycle, which with our processor is 125 nanoseconds, which tells us that we need 6 instruction cycles to enforce that delay. Next delay is going to be 2500 nanoseconds divided by 125 nanoseconds. So we see that's going to be roughly 20 instruction cycles. And then the last one, simply divide that through, and we find we're going to need a hell of a lot of instruction cycles to do that 120 millisecond delay. So we're going to use 3 different mechanisms here to do those real-time synchronizations. So effectively we need it to write 0 to port to pin P87, we need it to wait 6 instruction cycles, write 1 to P87, wait 20 instruction cycles, write 0 to P87, and wait 960,000 instruction cycles, then write 1 to P87. So that's sort of the software that we're going to need in order to mimic that waveform on P87. So the first bit is easy. Simply to do our 6 instruction cycles, we simply put 6. So we simply clear port H, so we do a bit clear on port H, we simply clear the most significant bit. We then have a delay of 6 instruction cycles. Then we set PTH, so then we do a bit set on the most significant bit of PTH, so we make that bit go high, and then we simply do our 6 instruction cycles. So it was 4 times x minus 1, which is 20, so therefore it's 4.75, and we round it up, which gives us 5. Okay, so we simply do our delay in that loop, and therefore once we've done that loop for our 20 instruction cycles, we then simply do our bit clear, which simply clears that line, which brings it low again. So now we need to do our slightly bigger loop. So therefore we've actually loaded y with 10, we've loaded x with 21,000-ish, and then we've simply done that for it, which will generate our 960,000 instruction cycle delay. So when I came to calculating those magic numbers for that loop, I've simply said I want to do 960,000, and then I've simply picked a number for one of our registers. So I've simply said, let's say we'll make y 10, and therefore I've solved what the value of x has to be, given that the value of y is 10. So therefore I've worked out that x would have to be 23,000. So it's simply pick a number for one, pick it big enough so that you know you're going to fit it, and then simply pick what the next value is going to be for the other register. Okay, so another software synchronization mechanism that we can use is of course polled I/O, and this is basically because some devices are a lot slower. Again, we don't have they don't follow a timing diagram. Let's say we give an instruction to a particular device. That device can take a nanosecond to do it, could take 10 nanoseconds, could take 100 nanoseconds. We don't know how long it's going to take for it to do that particular instruction that we've given it. So therefore we have some mechanism of finding out when it's ready. Okay, so basically we have a status bit from that device, so therefore we might send a device a particular piece of data, and that device may in fact have a series of status bits that we can then poll to see if in fact it's ready for the next bit of data. So that's why we call it polled I/O, is because the device makes available to us a status bit that we can then check to see if it's ready for the next piece of data. So the status register for that particular device will contain a bit-sized flag to tell the microprocessor when in fact it's ready for some new I/O, so whether it's ready to send I/O back or ready to receive a bit more I/O. So therefore, in order for the microprocessor to know when the device is ready, it needs to constantly check the status bit before communicating with the device. So even a lot of our internal I/O subsystems that we have, they operate a lot slower than the processor, so a lot of them have status bits that we then check and we poll, and we make sure that we don't hammer them with too much data. We make sure they're ready for new data before we give them more information. So the act of continually checking that status bit is commonly referred to as polling, because we simply keep polling, we keep checking, we keep looking to see if that bit's changed. If it hasn't, we keep looking. Once it changes, it's like, the device is ready, let's give it some more data. So to give you an example of this, I've got an I/O device, and I've basically hooked up that I/O device to port A, so I can simply send it a chunk of data through port A, and therefore the I/O device sends back through pin 7 of port B to tell me when in fact it's ready for new data. Okay, so I simply set up the data directional registers for port A and port B. I then simply load my data into accumulator A. I then branch to see if that device is actually ready for that bit of data. So I branch if clear. So simply, as long as that PB7 is 0, I simply branch back, do a spin lock while that bit is 0. The device will actually tell me, the I device will actually tell me when it's ready for data by simply making that flag go high. So when that flag, when PB7 goes high, I know the device is ready. I simply break, it will automatically break out of that spin loop on the wait line, and therefore I can simply store that data into port A. So therefore I've actually spun on the spot, polling that status bit to see when the device is actually ready. And it's the same thing when you actually write data to the serial device. Before you use putchar, the putchar subroutine actually polls the status bit to see when in fact the data transmit register is empty. When the data transmit register is empty, then it writes the data to that I/O device. If it's not ready, it simply sits there polling that status bit, waiting for it to become ready. Hardware handshaking is a bit of a sort of, a bit like polled, but therefore we have a bit of feedback letting us know whether things have actually happened right. So when a processor is talking to an extremely slow device, or it is extremely important that information is transferred correctly, then hardware handshaking may be used. Hardware handshaking consists of two devices talking to each other. The first system requests the information from the second system. The second system then notifies the first system when the information requested is ready to be read. The first system then reads the information and acknowledges that it has read the information. So it's a bit of a two-way street. So it's a bit of a slight extension on top of polled I/O. So in this example here, I've got the green bit where we set the request flag, the brown bit where we simply wait, the orange bit where we simply transmit, move the data out, and the silver and the purple bit where we actually do our acknowledgement. So first of all, we set up our data directional registers. We simply move the configuration word onto the data directional register of B, so we simply set all the pins to be output except for the PB1, which is set to be input. We then simply will do a few nops to wait for a while. Then we do our bit clear, so we tell the device, we basically set our request flag to tell the device we're actually after something, and we simply spin on that spot waiting for it to become ready. So we simply wait for the data, so we wait for the request or the ready flag to become high. Once the ready flag becomes high, then we simply go and read the data. So we're simply waiting for the device to make that data ready. Once we get it, once the device says, yeah, the data is ready, we then simply read the data from port A. So we move the contents of port A into a variable called data. And then we simply set the acknowledgement. So we do a bit set. So we set the acknowledge flag, we set it high. We delay for a couple of instruction cycles. So we leave that flag high for 2 instruction cycles, then we clear it, and then we've finished our code. So simply using that example, we've simply requested a flag, so we requested a bit of data, so we've kept that request flag high for 2 instruction cycles and brought it low. We've then waited for the device to tell us that it's got some data ready, so therefore when the data is ready, we simply get told, and we simply exit that branch always clear loop. And then once we've branched it, exited that loop, that means the data is ready to be read, so we simply read the data into port A, and we put that value in port A into data. We then simply set our acknowledgement flag to tell it that we've actually read it. So therefore the device can then no longer pump out that value out of its data port, so to speak. So I hope that's been an illustrative example on how parallel I/O works, or handshaking works. So like before, should you require any further assistance, please do not hesitate to ask your demonstrator, post a question on the forum, email me the convener, make an appointment to see me, ask me after the tutes or the lecture, or come see me in my office, but whatever means is best for you, please ensure that your questions get answered.